I'd like to thank everybody for attending today's webinar called Concrete's Environmental Impacts and Ability to Impact a Company's Environmental, Social, and Corporate Governance Goals. This is currently an extremely hot topic in the industrial warehouse building market, as you're going to hear today from Luke. This webinar is hosted by the Illinois Ready Mix Concrete Association. My name is Theron Tobalski, and I am the Assistant Executive Director for the association. A lot of what I do is work with the engineering community to promote all different types of concrete, and we're here to be a source of information and help whenever the engineering community needs it in regards to any type of concrete. This is the first, this webinar is part of a three-part webinar series. There are 12 webinars in total in this series. All of them can be found at www.irmca.org. You click on the webinars tab. It'll list all 12 webinar titles, dates, and speakers. Then you click on the read more option. It'll allow you to register and sponsor when the registration opens. Registration typically opens 14 days prior to the webinar. All these webinars will be recorded. Also on the website, on the webinars page is sponsors. When you click on the sponsors on the webinar page, you will see a lot of the sponsors have put some additional links of information they would like you to read. A lot of these links are to new technologies that are in the industry for engineers to listen and look at and specify. So these are a great source of information. And with that, we'll go ahead and introduce our speaker for today. Luke McHugh is the PE Senior Director, Local Paving National Ready Mix Concrete Association. He has over 30 years of experience providing consulting, engineering, and construction support services on a variety of airport and site development products. He earned a bachelor's degree in civil engineering from Drexel University in 1987 and a master's degree in engineering in the management from Drexel University in 2005. Luke is a registered professional engineer in Pennsylvania, New Jersey, Delaware, Maryland, and Florida. In his role at NRMCA, he's responsible for working with NRMCA partners, members to help deliver successful local concrete paving projects, implementing strategies that increase the use of various forms of ready-mix concrete in parking areas, local streets and roads, and other applications. And with that, I'll turn it over to Luke.
Okay, thanks, Theron. Get my screen up here. Okay, I hope everyone can see that. Okay, so let's get started. As Theron said, this is part one of a three-part series, and we'll talk a little bit more about the upcoming series after this. Okay, there we go. So a little bit about NRMCA. We're a national trade association whose membership is derived from the concrete ready mix producers across the country and other related industries, suppliers, and manufacturers. Our mission is basically to serve the industry and partners through several actions, including promoting the use of ready mix products in both buildings and paving through our Build Ahead, Build with Strength, and Pave Ahead initiatives. For those interested in becoming a member or associate member, you can go to our website under memberships. So I'm one of 7 individuals on the Pave Ahead team working around the country. I'm responsible for the Northeast, which includes Illinois, and work closely with Theron throughout the year. So, as you guessed, We're going to start off today talking about light bulbs. So way back in 1878, Thomas Edison invented the incandescent light bulb, which is almost 150 years ago. This was state of the art for almost the first 100 years. In 1976, Edward Hammer invented the pigtail fluorescent bulb as a result of the 1970s energy crisis. And before that, in 1962, Nick Holonyak invented the LED bulb. The pigtails and the LED are now common, but it really wasn't until the energy crisis that people started thinking about conserving energy. That was 50 years ago, and hardly anyone at that time thought about global warming. So let's compare the incandescent to the LED. So the LEDs, have a slightly higher initial cost, and that comes with some obvious benefits. They have an increased lifespan, so we replace them less frequently. They use less energy. The LED is 6 watts, and that's equivalent to a 60-watt bulb. They're cooler, so you're not heating your house when you're not heating your house with light bulbs, or burning your hand if you touch it to remove it. Overall, it's better for the environment. So even though the regular old light bulb was good, LEDs are better. The same can be said for concrete pavement. It could have a slightly higher initial cost. Today's concrete mixes use improved materials and processes. They last a long time with little care or maintenance, so we're not repairing potholes or repaving frequently, thus expending more energy and generating more CO2. They require less energy to build, so also less CO2. Indirectly, they provide energy efficiencies, saving money and energy. So like the LED bulb, even though asphalt pavements are good, concrete pavements are just better and better for the environment. By nature, concrete pavement is both resilient and sustainable. There are a number of concrete pavement options available besides the well-known full-depth conventional concrete pavement, each of which contribute to resilience and sustainability in its own way. Concrete overlays of existing asphalt pavement utilize the existing asphalt pavement as base support. So pavement removal costs are eliminated and thinner concrete pavement sections reduce construction costs. Ultimately, the resulting pavement has all the benefits of a full-depth concrete pavement. Concrete overlays are also not new. They were actually introduced in the 1920s and came to the forefront in the 1940s, first used in farm-to-market roads. Roller compacted concrete has been successfully used for shoulders, medians, driving lanes, and a subbase for flexible pavement, providing greater support than typical aggregate-based materials and resulting in stiffer pavement, which we will learn in a bit has several advantages. Full depth reclamation using cement slurry is a method of flexible pavement reconstruction that utilizes the existing asphalt pavement and or the subbase material and stabilizes it to provide stronger support for a new wearing course. The slurry, which is delivered by a ready-mix concrete truck, reduces dusting that is associated with dry spreading methods. Durability is a key factor in sustainability, and concrete pavements are durable. They have a proven long life. Because it's rigid pavement, concrete is not susceptible to potholes, which I'm sure many of you are experiencing today. They're also not susceptible to rutting and shoving. Concrete evenly carries the load and is resistant to freeze-thaw. We have said for years that concrete pavements are environmentally friendly. concrete uses fewer raw materials and no hazardous materials in production. In fact, recycled materials are commonly used in the form of supplementary cementitious materials like fly ash and slag cement. Because it is not petroleum-based, concrete pavement conserves our petroleum resources. You'll learn in a bit that in its use phase, concrete also plays a significant role in reducing fuel consumption. Stormwater runoff across the concrete pavement is also cleaner and cooler. Concrete's lighter color provides greater reflectivity and less heat absorption, thereby reducing the urban heat island effect. In fact, concrete pavements can lower the ambient air temperature by as much as 7 to 10 degrees. Every 1 degree change in temperature is equivalent to about 1.5% change in energy consumption. Albedo is the measure of the refraction of solar energy reflected by the Earth's surface. As you can see by this graph, normal concrete pavement performs better than asphalt pavements, including those with high albedo coatings. A reflective concrete pavement will be the most sustainable pavement. Think about this. If all roads nationwide were converted into reflective pavements, it would be equivalent to removing nearly 9.4 million, or roughly 8% of all passenger vehicles. Concrete pavements can reduce the global warming potential by as much as 50%. Concrete's higher reflectivity also reduces lighting requirements by nearly 25%. That equates to annual savings in energy costs. Concrete's reflectivity also enhances the performance of exterior LED lighting. The light poles in the lower photo were retrofitted with LED lights. And you can see the halo effect caused by the poor reflective surface. As one lighting engineer noted, dark color pavement just swallows the light. Before we go too much further, I want to clear up one thing, that there's a lot of misconceptions about concrete and sustainability. But the truth is that concrete has been and continues to be one of the world's strongest, most innovative, resilient, and sustainable construction materials available. This program will highlight several of the concrete industry's innovative and technological advancements that are playing a critical role in how we are building a more sustainable future. In their 2015 reference document towards sustainable pavement systems, the Federal Highway Administration defines a sustainable pavement as one that will, 1, achieve the engineering goals for which it was constructed, 2, preserve and restore surrounding ecosystems, 3, use financial, human, and environmental resources economically, and 4, meet basic human needs such as health, safety, equity, employment, comfort, and happiness. There are numerous focus points which are considered when evaluating pavement sustainability, such as energy consumption, depletion of non-renewable resources, or impacts on habitat. Perhaps one of the highest profile sources of greenhouse gas emissions. But that doesn't mean that any of the others are any less important. Taking all these impacts into consideration has created a paradigm shift in the design and construction community towards life cycle thinking. Life cycle thinking is a systemic framework that takes a holistic view of the production and consumption of a product and assesses its impact on the environment. Life cycle thinking goes beyond the traditional focus on production site and manufacturing processes to include environmental, social, and economic impacts of a product over its entire life cycle. Life cycle thinking can make it possible for a product to reduce its resource use and emissions, thus improving its socioeconomic performance. Life cycle thinking is made operational through life cycle management, an approach that puts the life cycle thinking tools and methodology into practice. A life cycle approach enables us to make more sustainable choices for the longer term. Many decisions in practice are already based on life cycles approach. For instance, consumer purchasing decisions via eco labels, company reports on environmental and social issues, like business design of products and services via life cycle assessments, and total cost of ownership using life cycle cost analysis and calculations. While both play key roles in life cycle management, life cycle cost analysis and life cycle assessment must not be confused with one another. Life cycle cost analysis looks at the economic considerations and provides a projected total ownership cost throughout the product services life. Life cycle assessment is concerned with the environmental considerations of a product and looks at its impact from cradle to grave. So when applying life cycle management to pavement design and construction, it's important that all participants throughout the process embrace life cycle thinking and have both the opportunity and the responsibility to conduct life cycle assessment as it pertains to their scope of their project. The cement and concrete industries are doing just that. Considering that concrete is the most widely used construction material, it is important that the industry take a leadership role in sustainability. So how does concrete help a company meet its ESG metrics or goals? Well, first, let's take some time to understand what we mean by ESG. It's a company's self-proclaimed approach and commitment to a variety of environmental, social, and governance issues like those you see here. With some of the major players in the warehousing and delivery sector, one of the first things you'll notice on either their website or their main page, their website main page or their About Us page, is their commitment to corporate responsibility and sustainability, their ESG. It's not surprising that in a 2019 ranking by Investors Business Daily, Prologis ranked number 3 overall. You get the sense just from their logo that sustainability is important to them. With respect to concrete, environmentally, we are concerned about emissions. There are quite a few, but the elephant in the room that is front and center is carbon dioxide, the primary contributor to global warming and a catalyst to life-threatening natural disasters. We can relate that to melting polar ice, to rising sea levels, or warmer seawater to stronger hurricanes, and drought to more frequent wildfires. In the warehousing distribution arena, emissions directly from building operations in company-owned vehicles or indirectly, like running a facility that is greener, change how and when employees commute or implementing systems that allow efficiencies, like changing the quantity or type of capital goods used and looking at efficiencies in all areas of the transportation distribution network, both upstream and downstream. So many of these enhancements focus on the building, especially when trying to achieve a LEED certification. So it could be cool roofs, skylights, smart energy meters, a secure biking shed with e-bike parking, or drought-tolerant plants and rainwater collection. But just having concrete pavement around the building could be as much as or more the footprint of the building itself and can contribute directly and indirectly to the reduction of CO2 emissions. So, think about lowering the cement content in the pavement or using recycled crushed concrete in the base course, and lowering the heat island effect that you have around all that pavement. As we said, concrete is one of the most widely used construction materials. So it's important that cement and concrete industries take a leadership role in that sustainability. In other words, how can we improve concrete to further reduce emissions? So let's talk a little bit more about the elephant in the room. It's widely accepted that for every ton of Portland cement manufactured, there's also 1 ton of carbon dioxide produced. When the pro-embodied reduction interests expressed their concern of concrete being a glutton of embodied CO2, they're actually only looking at initial embodied carbon from Portland cement. You could say that they fail to apply life cycle thinking as they fall short the complete life cycle assessment for concrete. 50 to 60% of the CO2 produced comes from the calcination of calcium carbonate raw materials and has nothing to do with the consumption of fossil fuels. Additionally, concrete actually absorbs CO2 throughout a process called carbonation. Over its life, concrete can absorb enough CO2 to offset 30 to 50% of the total CO2 initially produced. We also need to remember that a 1-to-1 ratio of CO2 refers to Portland cement, not Portland cement concrete. So 1 cubic yard of concrete typically has 420 to 650 pounds of cementitious materials. If we factor a 15 to 30% replacement of Portland cement with supplementary cementitious materials like fly ash and slag, we can calculate the embodied CO2 for 1 cubic yard of concrete is between 170 to 480 pounds. That alone is less than 15% of the total weight. So if we look at the whole picture and apply life cycle thinking, we see that the elephant does indeed easily fit in the room. So as an industry, we continue to work toward lowering concrete's carbon footprint. In fact, NRMCA producer members have lowered their carbon footprint by 13% since 2014. NRMCA has accepted Architecture 230's challenge for products with a goal for the materials industry to reduce carbon footprint by 50% by 2030. Did you know that 1 mile, that building 1 mile of 1 lane of road uses conventional construction methods and the standard flexible, 1 mile of a 1 lane road using conventional construction methods and the standard flexible paving materials uses as much energy as 100 American households do over the course of an entire year. This is one of my favorite slides. So this is a graph that was put together, I believe, by the folks at MIT. And when you look at concrete compared to all the other building materials listed on this graph, you can see that it's a low impact material down in the lower left-hand corner. The chart shows a variety of different materials plotted according to the embodied carbon dioxide on the y-axis associated with producing the materials, and the same thing on the energy scale, which is the x-axis. So that's the amount of energy required to produce that material. It's a log scale increasing by a factor of 10, and concrete and cement are much lower than a vast majority of these materials. So let's just take a look at this. So here we have where we've got bituminous and asphalt, and you can see where cement and concrete fall relative to that. Looking at the maximum amount of energy required to manufacture the bitumen, you can see it's in the neighborhood of almost 9 to 10 times that of cement. When we correlate that to embodied carbon, they're generally within the same area or arena. Likewise, we'll take a look at the final product, the paving product of asphalt versus concrete. And you can see there that you're anywhere from about 3 to 5 times less energy required to manufacture concrete than you do with asphalt. So, you know, decoupling material production impacts is something we need to do from the volumes that we use. So even though it's very low compared to asphalt for a concrete pavement, concrete itself is used so much that it should be on our radar. Long before sustainability became a driving force, concrete producers were using supplementary cementitious materials, or SCMs, to enhance properties of concrete. They improve workability, greater durability due to increased density, a higher overall strength, and alkali silica reactivity. Mitigation were some of the reasons that concrete mixes included SCMs. As our previous example showed, the use of supplementary cementitious materials can also have a positive impact on lowering concrete's embodied carbon. Through the efforts of both the cement and concrete industries, there are numerous solutions available today for lowering concrete's environmental impact. These efforts, bolded here, have been in use for a number of years and have already had a positive impact on lowering concrete's carbon footprint. In the next few slides, we'll take a look at some of the newer technologies and products available. The first thing we'll look at is Portland-limestone cement. It's a blended cement with additional limestone content, which is optimized for performance. While regular Portland cement contains up to 5% limestone, Portland limestone cement is made by intergrinding 15% limestone with a reduced amount of regular clinker, the main energy-intensive ingredient in Portland cement. Remember that we said 50 to 60% of the CO2 produced was attributable to calcination of calcium carbonate. Reducing the amount of clinker per ton of cement reduces the amount of attributable carbon dioxide. Portland limestone cement is a finer ground product than regular Portland cement. So the smaller size produces a particle packing effect that increases the resulting concrete strength. Portland limestone cement gives specifiers, architects, engineers, producers, and designers a greener way to build any structure, paving, or geotechnical project with virtually no modification to mix design or placing procedures, all while highlighting resilience and sustainability. Typically, Portland limestone cement can reduce the concrete's carbon footprint by about 10%. Transportation infrastructure has seen quite a bit of Portland limestone cement usage. Several state DOTs in the US have a good success placing Portland limestone cement concrete pavements for more than a decade. And it's appropriate structural concrete for bridge applications. Everything from the deck down to the foundation, including geotechnical work. Portland limestone cement can be specified as ASTM C595 type 1L or AASHTO M240 type 1L. You can find more information about this on greenercement.org. Another new technology is enhanced carbonation, also known as carbon capture or carbon sequestration. Carbon sequestration technology is a promising solution to reducing the carbon footprint of cement and concrete while improving performance. Many carbon capture and sequestration technologies are already commercially viable and are currently being used for construction, since they can be conveniently produced by existing equipment or by retrofitting existing factories. Overall, carbon capture offers a simple but highly promising solution to reducing the environmental footprint of concrete. In simplest terms, enhanced carbonation involves injecting CO2 into the cement, aggregate, or concrete, creating calcium carbonate, in effect, a synthetic limestone. And in the process, a small amount of CO2 is sequestered. Applied to cement production, Enhanced carbonation has several positive impacts, including lower resource consumption, lower manufacturing temperatures, which in turn result in reduced energy consumption during production, reducing greenhouse gas emissions by 30%, and can reduce concrete's carbon footprint by as much as 70%. Enhanced carbonation can also be applied to aggregate production. Carbon sequestered aggregate consists of coating of calcium carbonate synthetic limestone crystallized on the surface of recycled aggregates, such as crushed recycled concrete, giving it a smoother surface finish. Using carbon sequestered aggregate can offset roughly 600 pounds of CO2 per cubic yard. Again, looking at our previous example of embodied carbon per cubic yard of concrete, that's more CO2 than is attributed to the initial cement production. Other commercially viable technologies accelerate carbonation of concrete. This is accomplished by either injecting CO2 into the concrete or curing concrete in CO2. One company, CarbonCure, uses CO2 capture from industrial emissions, which is then purified, liquefied, and delivered to partner concrete plants in pressurized tanks. This is then injected into the concrete while the concrete is being mixed, which converts the CO2 into calcium carbonate with the concrete. The process reduces CO2 emissions in two ways: through direct sequestration of CO2 injected into the concrete, and by reducing the cement demand, since this concrete requires less cement to produce concrete at a specified strength. Studies have shown that enhanced carbonation typically enhances concrete's compressive strength while reducing cement content. Quick recap on the different types of carbon emissions, maybe referring to embodied carbon and operational carbon. So embodied carbon is the emission of carbon dioxide that's used in the building phase, including material extraction, transport, construction, renovation, and demolition, while operational carbon is the emission of carbon dioxide during the operation or use phase of a building. In addition, some of the CO2 reduction strategies we have already examined, CarbonCure has found that an additional 20 to 35 pounds of CO2 can be mitigated by injecting carbon dioxide into concrete during the mixing process. Depending on the application, these reductions can be achieved by using one or any combination of these strategies. So you're not limiting yourself to any one. They can be combined to maximize or optimize your concrete mixture. With respect to fuel savings, the EPA and MIT correlated the reduction of CO2 emissions at a commercial facility looking at the relative number of trucks and miles traveled in a year, and just by driving on a concrete pavement instead of an asphalt pavement. So if you look at this graph here, you'll see that if you have 350 trucks a day, which are shown by the green bars, and that truck is driving 1 mile on a facility, you can save or reduce carbon emissions by over 2.3 million pounds in a year just by using concrete. And if you think about it, a one mile is about one loop around a 1 million square foot warehouse. Similar to CarbonCure, a team of researchers managed by UCLA began working in 2014 with the aim of producing CO2 neutral cement. Their process works like baking a cake, capturing CO2 from flue gas, injecting it into a chemical reaction with other elements, and producing carboncrete. By utilizing industrial wastes, low-grade heat, and CO2, they are able to deliver cost savings while eliminating the need for extrinsic processing energy. Furthermore, the process offers the ability to produce cost-competitive cemented solids that can be carbon neutral or better, while achieving functional equivalence to traditional concrete. Prescriptive specifications can often limit the ability to apply new technology. Standard prescriptive specifications, such as restrictions on supplementary cementitious material quantities, minimum cementitious content, and other restrictions, limit opportunities to introduce new products and technology. Such specs also limit our ability to reduce concrete's environmental impact. Performance-based specifications are the best way to incorporate new technology and spur innovation. Each project may have multiple concrete mixes that meet specific performance requirements. Transitioning to performance-based specifications requires collaboration to share planning and risk among all participants. This can be implemented today if we can change our specification paradigm. The MIT Concrete Sustainability Hub is a dedicated interdisciplinary team of researchers from several departments across MIT working on concrete and infrastructure science, engineering, and economics since 2009. The Concrete Sustainability Hub uses a holistic approach in researching sustainable benefits of concrete for structures and pavements and developing tools to support the infrastructure decision-making process. For pavements, Concrete Sustainability Hub research focuses on improving structure and design that can result in increased fuel efficiency, lower maintenance costs, and better life cycle planning. One way to apply life cycle management to pavement design is to incorporate low impact and resilient design. Currently, life cycle bill of activities and life cycle assessment, or life cycle assessments and life cycle cost analyses are developed only after construction and therefore have little influence in the final pavement design. Research through the Concrete Sustainability Hub aims to integrate the bill of activities and life cycle assessment and life cycle cost analysis into mechanistic empirical design principles in order to promote smarter pavement design decisions before construction. Ultimately, pavement design optimization saves money and can aid in reducing greenhouse gas emissions and global warming potential. The Concrete Sustainability Hub has also determined that the use phase is just as important to sustainability as the design and construction phases, particularly with regard to pavements. Inclusion of the use phase is absolutely necessary if you want to obtain true cradle-to-grave life cycle assessment. The distribution of impacts over the life cycle tends to be correlated with traffic volume. High volume pavements may have large impacts from traffic-related components, whereas impacts from low volume pavements will likely be dominated by material-related components. The Concrete Sustainability Hub conducted a life cycle assessment of 3 model scenarios: high, moderate, and low volume roadways. The functional unit was 1 mile of roadway, and the analysis period was 50 years. They compared asphalt and concrete in all 3 models. The research showed the importance of pavement-vehicle interaction in relation to a pavement's measure of sustainability. Pavement-vehicle interaction is a concept that looks at the interaction between a vehicle's tires and the roadway surface on which it's driving. It's also known as rolling resistance. 3 factors relating to a road surface condition and structural properties contribute significantly to pavement-vehicle interaction. Roughness, which refers to how bumpy or how smooth a road is; texture, the abrasiveness of the road surface; and deflection, or the bending of the pavement under the weight of the vehicle. Our pavement parameters considered are pavement type and structure, traffic patterns, pavement temperature. Pavement stiffness relates to how much energy is needed to move a vehicle as the pavement deflects and the vehicle is pushing pavement, and it is as if the vehicle was always moving uphill. The Concrete Sustainability Hub quantified excess fuel consumption due to pavement vehicle interaction primarily through road stiffness and roughness. The environmental impacts of pavement vehicle interaction are significant for pavements over time. Stiffer pavement can result in as much as a 3% reduction in fuel consumption for trucks and as much as a 15% reduction for cars. Additionally, stiffer pavements can result in lower greenhouse gas emissions. Information about pavement vehicle interaction is not just important for designing an individual pavement, but also useful for monitoring and managing the pavement network as a whole. The analysis shown here surveys the performance of all Virginia no, I took out that slide, so we're going to forget about that one. So, in summary, we could say that sustainability can be affected at different stages. Material selection, design, asset management, or life cycle approach to maintenance and rehabilitation, important part of asset as an important part of asset management. Use phase is also a major contributor to overall sustainability performance, and there are various ways to disclose or quantify sustainability. The method chosen is dependent on the desired outcome. As I mentioned before, the goal was to be carbon neutral by 2030, with an ultimate goal to be carbon neutral in 2050 within the concrete industry. That concludes the formal presentation of today. I just wanted to make you aware of a couple of upcoming webinars. So you'll see that part 2 of the series, Portland-limestone cement, is scheduled for March 17th. Part 3 of the series, where Allison Palmer from Carbon Cure will be talking with also Ryan Cialdella from Ozinga on the use of Carbon Cure and how that can lower parking lot concrete in parking lots, lower emissions. And also, just going to give a quick shout out here to those of you who either missed or tried to attend the webinar prior to this one, how to design industrial light duty parking lot asphalt pavements. That is now rescheduled for March 25th. So be sure to sign up for those webinars when they become available. So Theron, I just want to say thank you for allowing me the opportunity to speak today. I've listed both of our contact information, and if there's any questions, I'll turn it back to you.
Thanks, Luke. Appreciate it. Good job on the presentation. There is one question that came up, Luke. I'll read it and see if you could answer it. Does the Carbon Cure process lead to less uptake of carbon by that concrete by carbonation over its service life?
Does the Carbon Cure process lead to less uptake of carbon by that concrete by carbonation over its service life? That's a good question, and I'm going to have to say that that's probably a better question for Carbon Cure during their presentation in 4 weeks. So you'll have to sign up for the next presentation to find out the answer to that question.
Michael, I'll reach out to the Carbon Cure group in the team and get you an answer on this. I will send an email out to everybody who attended with the question and the answer. Good question. You kind of stumped our experts, and as Luke mentioned, that's probably something we should go to the Carbon Cure team to get an answer on. So we will get this to you within the next week or so, an answer on that. With that, I don't see any more questions. We hope you enjoyed today's webinar. Our goal was to give the engineering community several different ways in which you as an engineer can change your specifications to allow your clients to meet ESG goals, to lower the carbon footprint of their projects, to allow different carbon reduction technologies. And with saying that, if this is something that you're interested in, you can always reach out to me. We'll work with Luke and the different teams needed to help you alter your specifications. There is a growing want of the concrete industry to use these type of technologies, but at the end of the day, it comes down to the engineering community changing their specs to allow these type of technologies. And that's kind of why we're here today. We're here to show you the different options and to educate you a little bit on them. And we also think it's a good method for you also to educate your clients on these different type of technologies. If you're looking for these type of webinars for your clients, you can always contact me. We can work with you and your clients to educate them on this as well. I think in the ESG world out there, not all the ESG experts really understand how concrete can help them meet their goals. So it kind of takes that education process to help them realize that, hey, there's a product out there that you have on most of your projects that can really help you meet those ESG goals. So with that, and I think we got another question that popped up. Okay, that was Mike saying thank you, that he appreciates us getting an answer back to him via email. With that, again, as Luke mentioned, we have another webinar coming up on the 17th and then on the 25th of this month. Registration will open 2 days from now for the webinar next week. With that, I'd like to thank everybody for coming today. With that, we'll be ending the webinar.